All right. For the purpose of the recording, hello, I'm David. I'm the coordinator of the Maths Learning Centre. It is semester 1, 2022, and this is a revision seminar for Algebra 2. I don't always do one for algebra, but this year I thought it would be a good idea. So here we are. I've had some requests. It's going to be some serious work for me to remember some of these things, and so that's probably a good thing to see how to figure these things out from scratch, probably. So I've been asked about dual spaces and the first isomorphism theorem, simple groups and inner products and proof techniques. All right. I'm going to start with the proof techniques and just say a couple of random, vague things, and hopefully if we do some example proofs along the way, then we can figure them out as we go. Because one thing I do know is that the act of proving is not something one can learn in general. You learn it from a lot of specific examples. So, yeah. All right. Well, if you can tell me what the replacement theorem is, and we can prove it. Cool. But for the beginning of it, like the vibe of this whole being a pure maths course, it's about proofs. That is the whole point. Like applied maths has proofs too, and so does statistics. But pure maths is entirely made of proofs, definitions and proofs, basically. I mean, there's theorems, but theorems only exist because we have a proof of them. Otherwise, they'd be conjectures. So, and for better or for worse, that is where we are with pure maths. It's about proofs. And so a proof has to be it can serve many purposes. Many mathematicians think it serves the purpose of explaining the meaning of something, but for most users of proofs, doesn't. But it is supposed to be a convincing of the truth of something. And so you have to get from you have to turn the statement that there's like a statement, yeah. And then there's like a proof. And the proof, that statement has to be turned into what that statement is like in a proof. And I know that's a weird thing to say, but what I mean is if the statement says if then your proof generally goes suppose blah, 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 therefore. And if your statement is just there is a thing, then your proof has to go, here is the thing, and here is why it really is the thing. And so different kinds of statements end up with different shapes of proof. And if the statement is there is no thing, then your proof is usually suppose there is a thing, and therefore contradiction. And so proof has to be this statement, but in a suppose then sort of context. So the statement will be very, I don't know how to talk about the grammar of it, but the grammar will change. The way you talk about it will be different in the proof than the statement itself. But usually if the statement is like if blah, 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 then blah, 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 then the proof will go suppose blah, 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 working, 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 therefore blah, blah, blah. And what has to be and that's just an example of how the grammar of this becomes different when you talk about it here. And my big advice for proofs, which is the same advice I give for first years, is that one of the most productive things you can do is to write what you think the first line of your proof and the last line of your proof are going to be. It helps you focus on what it is you're trying to achieve. And in here somewhere, you must use either the definition or an earlier theorem. But almost always the definition. The reason we have the definitions that we have is precisely because they are the easiest thing to use in a proof. Because there are many choices we could have made for the definitions. We could have, I mean, some of them there's only one natural choice. You go, well, obviously that's what we would have had to choose for that definition. But there are some places where the definition could have been chosen differently. And the choice we've made is the one that makes it easiest to run in a proof. And so the definition of things is a useful piece of information to help you figure out how to prove them, because they were chosen to make proofs easier. And the theorems you use are usually named theorems, like the first isomorphism theorem or Pearson's theorem. They wouldn't have been given names unless they became useful for proving other things. Or they were just so spectacularly surprising and wonderful that people wanted to remember them. But it's usually because they were useful for other stuff. So I think that's just some general advice, and we can give some more specific advice as we go. And the other piece of general advice I would give is the advice that's on the Maths Learning Centre wall, on the problem-solving chart, which says, at any moment, or it doesn't say it this way, but a useful thing to ask yourself at any moment is, what does that mean? You need to know the meaning of the words and symbols on the page, not just the individual words, but what they mean together and what the symbols mean. So if you don't know what those things mean, you have no choice. You have no hope for solving the proof. But at any moment, you can either do algebra in the high school sense of rearranging stuff on the page, or you can ask yourself, the thing that I've just wrote, what does it mean? And I know that that seems a bit vague, but that's all I can say. So a useful question to ask at any point. Oh, damn it. Look at the thing on the page and say, what does it mean? And you don't have to ask it about the things at the beginning. You can also ask about the things at the end. And sometimes the answer to what does it mean is, well, they told me what phi or sigma was earlier on the page. That's what phi means. Or it says isomorphic. I've just written that these things are isomorphic. What does it mean to be isomorphic? Or it says one-to-one. What does it mean to be one-to-one? At any moment, you can usually ask yourself, what does it mean? And it can help you to progress. That's sort of the total of my advice for proofs at the moment. I can't think of anything unless I do an actual proof.
So, when would you go for
I don't have specific advice about that, but I will say direct proof is usually a good idea, especially for an if-then statement. Yeah, go if then and turn that into a suppose blah, 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 therefore. A contrapositive is suppose not and therefore not, right? You switch it around the other way. I will say that contrapositive or contradiction are easier when the thing you're trying to prove is already not something else. So if the thing you're trying to prove is that there is nothing, then it's much easier to suppose there is something and show that that's wrong. And if the definition of your object is not being something else, then it's easier to talk about something that is, not something that isn't. And so if the statement is not something, then a contradiction or contrapositive might be easier. So my example of that isn't from Algebra 2 because I don't have Algebra 2 in my head at the moment, but when you're trying to prove that a number is, like, prove things about irrational numbers, it's much easier to prove things about rational numbers because an irrational number is a number that cannot be written a certain way. And it's already a negative. It's already not something. And so it's easier to suppose that something is rational and show that that's bad than it is to suppose that something's irrational and not know how to write it, because irrational numbers are defined by not being able to be written a certain way. So that's my only advice I have. I hope it's useful. Yeah. Otherwise, it's just imagine both and decide and hope that it works. Okay. So let me talk about stuff. And now I need to make sure that you are aware that you can stop me at any time to put in extra information or ask more questions. That's always okay. Goes for you in the Zoom as well. I'm not going to say your name so it doesn't appear on the recording unless you want it to. Yeah, you're always allowed to stop me and put extra information in or ask questions or whatever. Okay. And I'm going to ask you things every so often as well, such as, what do you want to know about the first isomorphism theorem? I don't know. Can't tell you when you'd use it. What does it mean? Let's just talk it out. Yep. Yep. Okay, so let's just talk this out. So the first isomorphism theorem, according to your lecturer's notes, is not there. Let phi, which sends G to, all right, I'm going to write the theorem exactly as it's written, and then we're going to change it to understand it better. So let phi, which sends G to the image of phi, be a group homomorphism with kernel N. Okay. And then it also says, let theta, which sends G to G over N, be as in theorem 7.10, whatever the hell that means. Yep, it is. It is, but I'm just going to write down exactly as it's written down. Then there is a unique isomorphism sigma, which sends G factor N to the image of phi given by sigma Gn is phi of G. Okay, so the first thing we need to fix is what this as in theorem 7.10, 7.10 means. And 7.10 is saying that theta of the element G is the element Gn. Okay. Right. What's that? Yeah, I know. Sorry. That by that. Just copying what it said there. I've replaced this bit here, which says as in theorem 7.10, and replaced it with be given by theta of G is Gn, which seems to me to be almost the same number of letters. And I don't know why they didn't just say it that way in the first place. But anyway. And it's a homomorphism, right? Okay. Okay. Well, what does this mean? That's the big question. So just pulling apart some words. I've got this. The first thing I notice about this text is the word unique, meaning that there is exactly one isomorphism between the factor group G on N and the image of phi. So the very short version of this theorem is that the very short version of this theorem would be that if phi sends G to anywhere, doesn't matter where it is, if phi is a group homomorphism with kernel N, you're saying your question was that why is it saying G going to the image of phi? Doesn't G go to the image of phi always? That's what you're asking, yeah? Well, I reckon we can break that and it'll still work. G's allowed to go anywhere. Like, so the phi is allowed to send G to any other group. It's just that whatever group it sends to, it will send it to its image. And there will possibly be parts of H that are not covered by G, by the image of G. But we're allowed to say if phi sends G to H as a group homomorphism with kernel N, then what they're telling me is that there is an isomorphism between G factor N and the image of phi. Are there two equals in an isomorphism symbol or just one? Which one does he use in his text? Sure, I'll use both. It feels good to me to use both. This is the short version. The short version is that if there is a homomorphism out of G into any other group with kernel N, then G factor N is isomorphic to the image. That's the short version of the theorem. That is the key and most important information, is that there is an isomorphism between those things. The fact that it's unique is probably useful, but the fact that it exists at all is the important bit, I reckon. How are people feeling about what I just said? Yep. What's that? Draw it? Yeah, that's what I was going to do. So the first thing in my head is the drawing as well after this. So there is a group G, which looks like whatever the group G looks like, and it has an identity somewhere. I really want to finish this off to like... Sorry. my neighbor. Sorry. Yeah, just I put it in just the right spot. I just didn't mean to, but that's just what it felt like. And here is some other group H, and the homomorphism goes this way. And every element of G ends up somewhere over here as an element of H afterwards. So the picture I'm thinking is that here's my element G, and phi ends up over here, and this is phi of G. So that's what I'm imagining happens with a group. Like you get all the elements of G, and they all end up over here. And what will happen is the identity of G will go to the identity of H. That's how homomorphism are guaranteed to work. Just going to need to, this is the beginning. Just draw another picture as well. Yep. Correct. That's what I was about to draw. Yeah. No, it is completely true. The image of phi is a subset of H. It could be equal to H. Yep. So the image of phi is a subset or equal to H. While we're at that, just as an aside, the grammar is object like element. That's the official word. And that's the grammar. Well, elements are this in sets, and sets are this in sets. Well, that's also about sets in this context. So you have no. I mean, it is. I mean, technically the group is normal in itself, but nobody cares. So, yeah. So the identity would be a normal subgroup automatically, right? Okay, we'll talk about that, but all the left cosets are the same as the right cosets, right? Yeah. That's the definition, isn't it? Yeah, okay. So in an abelian group, everything's normal because, everything's the same on both sides. Okay, so these are all the same kind of thing. And technically, we can write this symbol with numbers, but, well, let's just reuse our symbols today. But this one is about a single element being in a set. And this is about a collection of things inside another collection of things. I don't have a good way of remembering it. I'm sorry. I guess that looks like a less than sign, but curvy. So it's like less than or equal to. Yeah. And in my head, this bit here is the same as this bit here. And this is a specific element here. Yeah. But yeah, it's like the grammar is that to write this is to say that this thing here is a set. I mean, it is actually short for E. Yes, it is. It is. It was originally an epsilon. This is one of the ways to write epsilon. Our modern version of the set membership symbol is not an epsilon anymore. It's slightly different to indicate that it is a different thing, but it is an E, short for element of, I believe, but it's probably Greek or something or Latin. But and this is a C for contained in. That's how I think of it. Yeah, so I like the extra line. To me is just making it more specific. This is general, this is specific. That's how I think about it. So anyway. Okay, so anyway, I'm redrawing this picture, but bigger. So here is my image of phi, which is somewhere in H, but not necessarily the whole of H. That's what you were saying. And what happens is that when you do phi on the entire of G, it all ends up here in the image. The whole of G gets squashed into here. The whole of N gets squashed into the identity. It's the kernel. So we were told that the kernel of phi was N. The kernel is everything that ends up at the identity afterwards. And so this is a more accurate picture of what's going on. And what happens is that each of the cosets of N end up at the points of the image. So G can be cut into cosets of N, which are the same shape as N, but cover G. I'm going to start thinking of G as a three-dimensional picture now. I should have done strips, but that's okay. Maybe I'll draw them as squares. Okay, here we go. Next picture. Yes, let's do this. No, I'll put the identity over here. This appeals to me for many reasons. Yep. Cool. I'm so happy. So the entire of G gets squashed into here. Okay. And the entire of N gets squashed into here. Yeah, so cool. N has cosets. We're dividing G up into its cosets of N. What that will mean is that each of these cosets end up as one of these images, one of these pieces of phi. They do collapse to a point. So an even better picture is probably this. that n will go to the identity of H, and each coset of n, the entire coset, will go to one of the elements of image of phi. All of these end up here, and all of these points end up here, and all of these points end up here, and all of these points end up here. I really would love this to be a 3D diagram. I have one more go. Ready? Whoa. Yeah, it'll work. So all of these elements end up here at the identity of H. And all of these elements end up here at this thing. And all of these elements end up here at this thing. So I just need more colors, just a second. So these all end up at the identity of H. It's all the same homomorphism. All of these lines are phi. Oh yeah, just wait. Yep, cool, cool, cool. Just wait. We're not there yet. I feel good about this picture. Yes. Okay. So this is what's happening. We haven't even got the isomorphism theorem yet, but this is what's happening, that there is this is part of what the theorem is doing. So far at the beginning, all we have is the orange lines. We know that the entire of n ends up at EH, and we know that n has cosets, and we know that and the theorem is saying that the whole of a coset will end up at the same place. And this coset will all end up at the same place as each other, and this coset will all end up at the same place as each other. And adding these two cosets together is the same as adding these two images in H together. That's what the isomorphism means. And the correct isomorphism is the one that takes one element of G and takes it to whatever this is. So, well, let me go back here. So for them to be isomorphic, G over N is these cosets, but the cosets themselves are considered as a whole one element of G over N. And this is made of things called Gn, like that. So G over N is going to the image of phi. And the way it's doing it is that the element G over N will become the element G of F phi of G. And this thing is called sigma. Just, I don't know if you've seen this notation, a single arrow is about a function taking an entire set to another set, and an arrow with a bar at the front is about a single element being able to produce another single element. Yep. No, the sigma function, so the colored lines are the individual elements of G, so they're the phi's, these colored lines. The sigma function is saying that the entire coset becomes this element. Yeah. and produce, so sigma function takes in a coset as an element and produces an element of H as an element, as an answer. An answer takes in, this is the element, this entire thing. Yeah. Okay, so phi of G is fine because phi, you're right. So you're saying that this coset, I could have chosen lots of different G's here, right? And so why is it okay for me to say the answer for this is phi of G? That's not well defined. Because you're saying if I chose a different little G, wouldn't that give me a different answer here? And the answer is no, it wouldn't, because the entire of this coset, all of these elements, phi of those elements is the same thing. So I choose this coset here, this pink one. Maybe I choose this G and I get that answer for sigma. But if I chose this G, I'd also get that same answer for sigma because they all give the same answer. The entire coset, every element of G in that coset, when I do phi, they all produce the same answer. So I can represent it as G of N. So if I choose, you know, G dash N for a different G, instead, 5G dashed is the same answer as 5G anyway. That's the point of this theorem. The point of this theorem is, like the big point, the point of this theorem is that if N is the kernel of phi, and G1 and G2 are both in the same coset, then phi of G1 will be the same as phi of G2. That's pretty much what this theorem is hinging upon. And so therefore, it doesn't matter how I define sigma, whether I use it as, you know, i.e. like G1n equals G2n equals Gn, like they're all the same thing. I could choose phi to be any one of the sigma of this coset to be any one of these, and it wouldn't matter because they're all the same thing anyway. And the theorem is saying that that's the only way to set up an isomorphism between the factor group and the image, is to do exactly that. Yeah, because it's unique. Yeah, but I think the theorem is probably reused in a lot of places where you don't explicitly construct the isomorphism. You just say, oh, they're isomorphic. Isomorphic. The theorem's probably used more in the sense of saying, I would like to show that these two groups are isomorphic. I'm going to show that this group is the factor group of that thing, and this group is the image of that thing, therefore they're isomorphic. Yeah. Yeah. So this is indicating how the proof works, probably, that I'm going to make an attempt. Possibly only-ish, but I'll give it a go. Suppose sigma, which takes G on N to the image of phi, is defined by sigma of the coset Gn is phi of G. So it says there is a unique isomorphism. That's this. They have told us how to define this function, but I reckon the proof is that we have to prove that it really is an isomorphism. And to be unique, we're going to have to show that any other isomorphism is the same one after all. Okay, I'm just going to give it a go. Here we go. And then we're going to do some work and we're going to go, hopefully there's enough room, maybe not. It's probably a big theorem. Therefore, phi is an isomorphism. Yay. Okay, and the uniqueness, I'm not going to do, but the uniqueness would be, to be unique, there has to be only one. And mostly the way to prove that there's only one is to suppose you have another one, and it's the one I first thought of after all. It's almost contrapositive, but not quite. But again, like, yeah, being only one is technically saying there aren't any others. So we go, well, suppose there are others. Yeah. Okay. So to be an isomorphism, it has to preserve group operations. And it has to be one-to-one, and it has to be onto. And so I'm going to have to prove all three of those. And so did you see what I did? I said, what does it mean to say it's an isomorphism? And that creates three smaller proofs. Yep.
That would only contain those finite number of points as to how many concepts there are.
Mm-hmm.
But then the image of phi, is that larger? Like
No, same thing. Yeah, and it's because it turns out to be the same. So it's because the whole coset end up as the same place, and so we end up with the same thing after all. Like these, all these arrows is saying what G becomes, and G becomes image of phi. But we've organized these arrows into cosets, and so we can think about them as acting on the cosets themselves. And that's what we call sigma instead of phi. Yep.
So, it's saying there is the homomorphism where well phi and then basically turn it to one.
Basically. Yeah, so 2D is cosets, a stack of cosets, and the cosets is sort of one-dimensional, but then all of these become points. And so you turn these lines into points. Yeah. And this is exactly how it works in linear algebra. Like when you do a linear transformation of Rn, like from R3 to R2, then you squash the whole of R3 into a plane. And so what you do is you divide R3 up into lines, and each line becomes one of the points on the plane. Yep, linear transformations can go from differently sized spaces to each other. You can go from where you are to yourself, and that's very special. That's an automorphism. Yes, of course you can't find my camera. I knocked it off the table. Please don't tell me I've broken the camera forever. We will start the camera program again. Oh, over here. Yes, okay, good move. Thank you. Yep, okay. You guys had the honor of being my last revision seminar this semester. 12. including this one. No, don't do third year. There's enough as it is for first and second year. Okay. I love this picture. I should take a photo of it and tweet it. That's exactly what I should do. Okay. I just love the sequence of pictures. It was my I'm so happy. Okay. So to show it's an isomorphism, I'm going to need three pieces. There's going to be the bit where I show that it's therefore it's a homomorphism. I'm probably going to have to show it's well defined as well, aren't I? Because that's a thing, isn't it? That's a thing that we are. Oh, crap. All right, so this is the shape of the proof now. All of these things we have to prove. Maybe do you want me to do that, or do you want me to not do that? Yeah, let's talk about other things. Cool. But at least this is the beginning of proving, is to figure out what has to be proved. And well-defined is a new thing that we've added in this course that we didn't exist before, we didn't know about before, which is any time where you have a worry where there could be multiple choices for what the output could be, multiple choices for how to calculate the output of a function, you're going to need to show that they always give the same result. Cool. All right. Well, wow, that was fun. Okay. Usually it happens with cosets, really. Equivalence relations? Yeah. Yeah. Yeah, but they're also cosets. So no, then in equivalence classes. But basically when there is more than one way to represent your object, and you use the representation to do the calculation, there might be different answers. And so just going to point that out since we've mentioned it. I am unlikely to split this revision seminar into pieces to tell you exactly. I'll tell you which bit I talk about when I talk about what, but I'm not going to put it in different places on the page. I'm just going to say it's the 2022 seminar. So well-defined, it's like you have objects represented in multiple ways, e.g. cosets. And the function is described using the representation. E.g. 5 G1n, like sigma of G1n is, for example. Then what you worry about is that using a different version of the representation of the same thing, you might get different answers. You worry that different representations of the input, no, I'll put that over there, might produce different answers. Or results. Because I might have, I could, for example, have a function of fractions, right? And it'll tell me what the numerator is. But if I put in a half, it'll tell me 1. But if I put in 2/4, it'll tell me 2. So that's not a well-defined function, right? Because the number a half has 2 representations, and each representation produces a different answer. So a function is only supposed to produce one answer for every input. It's not allowed to produce more than one. And so that's why we need well-defined. But if you produce the same answer anyway, it's well-defined. Yeah.
But for all representations of the coset, we can choose the
Yeah. So I'm just going to repeat that for the purposes of people listening online. For this one, when you do well-defined, you would have to say, well, no matter how you represent this coset, the result is always the same. But that's okay because of this. That's what we have to show, basically. Which will happen precisely because n is the kernel of phi. Yeah. Yeah. Do you want me to do just that bit to show it's well defined, or are we okay with me moving on from there? What's that? Yep, cool. Talk about other stuff. All right. All right. What did you want to know about simple groups? Dual space? Go. I might not get to the simple groups anyway. So. I mean, they're very important in like the history of group theory, but you know, they're not. What's that? Yeah. Okay. So my understanding of the dual space is you have a vector space. We should call it V. The field, does he uses like a double struck F, like a blackboard bold F. Yeah. BB stands for blackboard. It's how to write bold on a blackboard. Okay, cool. And you create all of the linear transformations from F to just the field. So from V to its field. And they call this a linear functional, I believe. Sure. But it is a function, and you want it to be linear. So we want a function, and we want it to be linear. I phi of vector 1 plus vector 2 is supposed to be the same as phi of vector 1 plus phi of vector 2. And phi of k times vector 1 is supposed to be k times phi of vector 1. doesn't really matter, whether it's k or whatever. So if you do addition first, it's the same as doing addition after. If you do scalar multiplication first, it's the same as doing scalar multiplication after. Cool bananas. If you take the collection of all of these functions, then they themselves also form a vector space. If you take the collection of all possible functions from V to F that are linear, then together those functions form a vector space. Yeah. I need an example, but yeah. So V star is a set of all such functions. And it is the dual space of V. It is a vector space as well. Hey. Don't know yet. Let me just bear with me. So this is what we think about. And they are called the linear functionals. And they're also called the dual space of V. Cool. Let's think about this for a bit. So R3 with field R. That's a vector space we're familiar with. We've been playing with that for a while, since before we knew what it was called. And so R3 is made of things with 3 coordinates that each have 3 all real numbers. And I could define, for example, phi sends V to R as phi of the number x, y, z is 3x minus 7y plus z, for example. This is a linear function. Do you believe that this is a linear functional? Definitely produces a real number. We take any set of coordinates, or technically take any set of coordinates, chuck them into this formula, it will definitely produce a number. If I add 2 vectors first and then do this calculation, it'll be the same answer as if I did this calculation first and then added the answers. But do you believe that? Like that. It would be phi of A plus E, B plus F, C plus G, which according to the thing would be 3 of A plus E minus 7 of B plus F plus C plus G, because they are the numbers in the X, Y, and Z position. But on the other hand, if I did phi of A, B, C, and phi of E, F, G, I would get 3A minus 7B plus C, and this would be 3E minus 7F plus G, and they are the same. This is the same thing as this. Because if I expand this one out, well, I can factorize this one, right? Yay! So no matter whether I could add the vectors first and then do the function, or I could do the function on both vectors and add the answers, and I get the same answer either way. That makes it linear. I technically have to check the scalar multiplication thing as well, but it does work. And so it's a linear functional. And you can imagine changing these numbers in these positions, and that would also be a linear function. I could make an 8 and a -17 and a 41, and that would have been a linear functional as well. It would have been a perfectly good function from R3 to R that satisfied this property. Okay, cool. I can add two of these functions to each other by just adding their answers. So if I had a second one, I can add the answers. I can say, well, phi1 plus phi2, the function called phi1 plus phi2 is the same as do phi1, do phi2, and add the answers. And that'll work fine. So I'm just going to do another one, you know. No, I'm going to get confused. Rho. Something like that. And so then I could say that a new function, I shall call it sigma as you suggested. If sigma is rho plus phi, then that would mean that that's telling me that sigma of x, y, z is rho of x, y, z plus phi of x, y, z, which is 3x, no, rho, sorry, which is x minus 5z plus 3x minus 7y plus z, which is a perfectly good linear functional. Yay. Cool. And so adding them produces a new one. It's a vector space. I can add these things in the way that you add functions, and I produce a new function that does the things that those functions are supposed to do. It's closed under function addition, which is for us vector addition, because I'm treating the functions as vectors. So what the functions do to the vectors can be added together. Yeah, and so it's a vector space in its own. I can multiply them by a number, which is the same as multiplying all the results by a number. Look very closely. This numbers 3, minus 7, and 1 are like coordinates. And this numbers 1 and 0 and minus 5 are like coordinates. And when I added these two functionals together, I added their coefficients. And so I could have represented these linear functionals as dot products if I wanted to. So I could have said five x, y, z is 3 minus 7, 1 dot with x, y, z. And that rho of x, y, z was 1, 0, minus 5 dot with x, y, z. Yeah. Yes, I'm deliberately using coordinates. Yeah, so to use coordinates, you have to make a choice of basis, yes. that is important because some function vector spaces, well, you only look at finite dimensional ones in this one, but all I'm saying is trying to convince you that the way that these functions add together is the same as the way that these vectors add together. In this context, we have that V star is actually isomorphic to the original V. Because the way that these functions add together is the same as with these vectors add together. And for finite dimensional spaces, I believe that V star is isomorphic to V. Pretty sure. Is that right? Sounds like a theorem.
Yeah.
Yep, okay. So you're guaranteed that the second dual space is isomorphic to the original, no matter what your vector space is. But I'm pretty sure if you're finite dimensional, your vector dual space is isomorphic to the original as well. Could be wrong, but I'm pretty sure. Let me just have a look at the notes. Okay. I have lost my place. What page are you looking at? Yes, I'm much further along than that. Ah. Cool. Okay. So I'm just going to share this screen so that our online people can see it. So the vector space of the linear functionals from V to F is called the dual space, and is usually denoted as V star. It has the same dimension as the original one. So if they're both finite dimensional, then they must be isomorphic because all finite dimensional vector spaces with the same field are isomorphic to each other. Yeah, but if they're not finite dimensional, then it's not guaranteed. Yep, that's the isomorphism. Yep. Okay. So you don't necessarily have dot products. Your vector space might not be an inner product space. But if it is an inner product space, then every linear functional can be rewritten as a dot product with a particular vector. I don't know if that's a theorem that you get to or not, but it is the truth. Yeah. So orthogonal projection, for example, is a linear transform, like not orthogonal projection. No, it is useful. You use it in differential equations. Yeah.
I'm still just staring on how you got from when you had the sort of coordinates from the
Oh, that was just me noticing that they look similar. That I haven't proved it's isomorphic. It's like it looks like they are. So when I did when I added them together, this vector plus this vector is this vector, which is exactly what happened when I did the calculation. The coefficients of x joined together and the coefficients of z joined together and the coefficients of y joined together. And so to get sigma, which was phi plus rho, this vector is that vector plus that vector. And so adding functions here is the same as adding vectors there.
I'm saying that the vectors are like
In R3, yeah. Yeah. And so there is an isomorphism between R3 and the linear functionals for R3, where the isomorphism would take the functional phi and produce the vector 3 minus 7, 1. Yeah. So the functional does to vectors what dot producting with the vector 3 minus 7, 1 does to vectors. And so I can say that this is related, is connected up with that vector, and this function is connected up with that vector. And adding these two functions is the same as adding those two vectors. Yeah. And I think that's what that theorem with the deltas and the sigmas and the one that I was talking about on page 15 was talking about. Yeah. So I'm just gonna write it down on my piece of paper, and then you'll be able to see what my piece of paper says. But V1 up to Vn, a basis for big V over F, and phi 1 up to phi n is a basis for V star over F. That's okay, I'm copying what's on the screen. So I'm copying this bit just here. Where phi I of Vj is 1 if I equals j, and 0 if I is not equal to j. Yep, that's the theorem. So theorem 2.28 says that if V1 up to Vn is a basis for V over F, then this set of functions is a basis for V star over F, where this function does this job. Where when you define your function in such a way that when you put the first basis vector into the first function, you get 1. But if you put any other basis vector into the first function, you get 0. And when you put the second basis vector into the second function, you get 1. When you put any other basis vector into that function, you get 0. Because the point of these functions, they're supposed to produce real numbers when you put the vectors in. So just to be the long version, phi 1 of V1 will be 1, and phi 1 of V2 will be 0, and so on. And what that means is that phi 1 of, A V1 plus B V2 will be A times phi 1 of V1 plus B times phi 1 of V2, which will be A times 1 plus B times 0, which will be A. And so what these functions do is they tell you what the ith coordinate is. So phi I of A1 V1 plus A n Vn is AI. They tell you what the ith coordinate is. Yeah. Which is really cool. Which is what dot producting with the basis vectors normally, with the unit, what are they called? It's what dot producting does. Like if you've got the standard basis vectors, that's what they do. They tell you that coordinate when you dot product with things. So very cool. So you can define these functions in this way that says that phi I tells you what the coefficient of VI is, and that's definitely a linear functional, because if you add two vectors together, then their coefficients of VI will also add together, and so that's good. And that is the basis. How do you feel? So I want to do this properly. So here is a basis. No. That is a perfectly good basis for R3. So we're saying that we should be able to make a basis for R3 star as well. And so I'm going to make the function. So this is V1 and this is V2 and this is V3. So phi 1 of any phi 1 of A 300 plus B 320 plus C 321 will be the number A. That's how we're going to define this function. And phi 2 of A 300 plus B 320 plus C 321 is going to be B, and phi 3 of A 300 plus B 320 plus C 321 is going to be C. These are the three functions I define, and they are a basis for R3 star. Yeah. Yeah. So yes, I'm going to repeat that. If you choose a different basis for R3, I would get a different basis for R3 star. But that's okay, because R3 has infinitely many bases, and so does R3 star. So they would link up with each other very neatly. And I just want to be clear that I want to know what these functions do. So if I wanted to know what phi 1 of, 945 was, I would have to write 945 as a combination of these three vectors. So that would be phi 1. So I would have to go 945 would be 5 lots of 3, 2, 1 minus. So that's 15. So we'd have to take off 6. And that's 10. So we'd have to take off 6. I don't know. I'm just making up stuff. This process I'm doing doesn't have to be copied. I'm just trying to figure it out. And so that would make the correct thing there. And so I'd be left with, so 15 minus 9 would be minus 6. So I'd have to add another 15 again, I think. Does this work? 15 minus, no, I won't. Oh, damn it. 15 minus 9 would be minus 6. Is that right? 15 minus 9 would be plus 6, sorry. And so I'd have to add another 1. So 15 minus 9 is 6, plus 3 is 9. 10 minus 6 plus 0 is 4. 5 plus 0. Yeah, okay. So this is it written as a thing. This is not how you would normally write things as linear combinations of each other, but I was just going, well, the only way to make this 5 would be to come from the 3, 2, 1. And so I made 5 3, 2, 1s, and then I took off something to get the right answer. And the only way to make this 6 would be 3 lots of the 3, 2, 0. And so then I could do that. And so that means that this is the same as phi 1 of 5 lots of 3, 2, 1 minus 3 lots of 3, 2, 0 plus 3, 0, 0, which would be 1, because it's the coefficient of the first of V1. You'd normally solve a linear system, yeah. And phi 1 of 945, sorry, phi 2 of 945 would be minus 3, because that's the coefficient of the second vector. Damn it, sorry. It's not efficient, but I'm just pointing, that's what these functions are doing. Those functions are saying that this thing with all the delta with this thing here is basically saying that when you do phi of something, it tells you the matching coordinate. And so in order to know what phi 1 of this is, I have to write it in terms of the basis. And then phi 1 will be the first coordinate, first coefficient, which would be 1. But phi 2 would have been the second coefficient, would be minus 3. Yeah. 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 That's the whole point. It tells you the coefficients of the basis vectors. And if you do that, if you make a function that tells you the coefficients of the basis vectors, then you can construct all other possible functionals from those. Yeah. 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 Oh, okay, cool, 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 cool. So we're saying that if we have, I'm just going to go back to that theorem. So if you have this 2.29 here, if you have a basis and you have the matching dual basis as just described, then, of course it is. So once you've got a dual basis, you can figure out how to write any vector as a linear combination of the basis. Because the point of the dual basis is it tells you what the coefficient of V1 is. So if you've got a vector V, phi 1 of V will be the coefficient of V1 when you write it as a combination of V1 up to Vn. And phi 2 of V will be the coefficient of V2 when you write it as a linear combination of V1 up to Vn. Oh, that's so cool. That is not obvious at all. Until now. Oh, wow. But it works backwards. If you want to figure out how to write your linear functionals as combinations of the linear functional basis, it works the exact same way, but backwards. Ah. So the backwards one is saying that if you have a random linear functional, a random function that goes from V to R, well, V to F, then when you want to figure out how to write it as a combination of this basis, then you just figure out what the linear functional does to the first basis vector. So I just want to try it, like just a second. Yep.
base pieces for V star,
Mhm.
why weren't they the bases?
No, they are functions from V to the field.
They are. So sigma, when you apply sigma, it gives you something to do, so that's the scalar. And then sigma itself is a constant. So sigma is like an addition of other functions.
So I'm just going to just talk that out. So we have, let's do it again. So I'm just going to do the second half of that. V1 up to Vn, the basis for big V, and they're vectors. And phi1 up to phi n is a basis V star, which means that each of these is a function that sends V to the field. These are all functions that send V to the field. Yeah. And so if I create, if sigma is a function which sends V to the field, so what that is a linear function, that means that is sigma is in V star. That's what is a linear functional that is sigma is in V star. So it is a random function that goes from V to the field. So it doesn't matter which one I want. And then because this is the basis for V star, it must be possible to do sigma by doing all the phi's and doing a linear combination of the answers. And so it must be possible to write sigma is something times phi1 plus up to something times phi n, which means because sigma is a function, that sigma enacted upon a vector is going to be for all V and big V. That the way to do the function sigma is to do all the functions phi1 up to phi n and get those answers and do an whatever times them and add them together. So that will be how to do it. And it turns out that the way to figure out what these correct numbers here are is to figure out what sigma of V1 is. Because sigma takes the vector space and produces something in the field. And so it turns out that the correct number to go in this spot is sigma of V1. And the correct number to go in this spot is sigma of Vn. And the correct number to go in the second spot is sigma of V2. No, there isn't. They are the names of functions. But I'm just saying that this is the truth, right? I don't have these in this, like in the course notes, that it's this, isn't it? Without the A's. But it's got sigma V1, yeah. I'm just separating it into two pieces. Yeah. Sigma is the name of a function. And to interpret what the function is doing, you need to know what sigma of V is for every V. That's what I'm saying. In the same way that sine is the name of a function. It's not a linear functional, but sine is the name of a function. And to know what sine is doing, I need to know what sine of x is. That's the same idea.
It's like thinking about the fives, and then all the ones that aren't.
So I just want to. So back in the other example I was doing. I made my phi's like this. This was my basis of these. And this is my basis of phi's. And the phi's told you what coefficients these were. So I know that if I want to write, like it's double Dutch though in this one, but like if I want to figure out what but back here, writing this vector as a linear combination of the basis vectors, the number in that spot is phi1 of this vector. But I can do it in reverse. I can say, oh, what was this theorem? Theorem 2. No, it is 2.29 because it's not a decimal. Right. Yeah. Anyway, this is only half of theorem 2.29. So if we go back to our other example, what if I had a random sigma that did this? Let's choose the sigma that I made last time, just so that I'm consistent. Minus 4x minus 7y minus 4z. Then it must be possible to write this, no matter what x, y, and z is, as something times phi1 of x, y, z plus something of phi2 of x, y, z plus something times phi3 of x, y, z. Okay, that must be possible. And the somethings are sigma of V1. So the correct coefficient to go in this spot will be sigma of the first basis vector. So this will be sigma of the first basis vector, which was 3, 0, 0. And so that'll be 4 times 3 minus 7 times 0 minus 4 times 0, which is 12. And so that's the correct number in that spot. And A2 will be sigma of the second basis vector, which is sigma of 3, 2, 0, which is 4 times 3 minus, damn it, I'm doing this whole thing off screen, minus 7 times 2 minus 4 times 0, which is 12 minus 14, which is negative 2. And so that's what goes in this spot. And A3 will be sigma of V3, which will be sigma of 3, 2, 1, which will be 4 times 3 minus 7 times 2 minus 4 times 1, which will be minus 6, which is what goes in this spot. And so what will happen is that I could have made my function out of these things. So that means that sigma of x, y, z is the same as 12 of phi1 of x, y, z minus 2 of phi2 of x, y, z minus 6 of phi 3 of x, y, z. Okay. And if I, and what that, so the short, we're saying that as functions, sigma is 12 of phi 1 minus 2 of phi 2 minus 6 of phi 3. Yeah. Ah. Are you all right? The theorem told me that that is what I had to do. Well, let's stop. Can you just finish your question? I mean, I didn't do a proof. I was just describing what the theorem was saying. Let's do it. Okay, okay. Looking up my sleeves. Okay, so just the proof of the second half. Yep. The first half of the theorem, we designed it specially that way. So we know that we designed, just a second. So V1 up to Vn is a basis for V. They don't use underlined in this course, does he? He does use in bold? Cool. Is a basis for V. And we defined phi I of A1, V1 up to AN, VN to be AI. That's the definition that we've did. That's what the definition in the previous theorem said, basically. That's the long and the short of it. And we know that that's a basis. You know, basis for V star. Okay, cool. So we would like to show that given any sigma in V, the correct coefficients are sigma of V1 and sigma of V2 and so on. That's the theorem that we want to prove. Okay. So let sigma be in V star, sorry, sigma in V star. And then at the end, we want to show somewhere down here, therefore, sigma is sigma V1 lots of phi 1 up to sigma Vn lots of phi n. That's the goal. It's okay? Cool, 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 cool. Now, since it is in V star, and these really are a basis for V star, it must be possible to write it as a linear, as some linear combination of those things. It must be, because it is a basis. I'm sure that the previous proof shows us how we could know that it really is a basis. Hopefully. No, phi, sorry. Just some B1 up to Bn in the field. So for me to be able to make that statement, and the reason I wanted to make that statement was twofold. One was, at this point, I could ask myself, what do I do? And the first thing I do to decide what to do is to go back to anything written on the page and ask, what does it mean? And what it means for this to be a basis is for this to be writable as a linear combination of those things. That's what a basis is for. And that was nice because it matched up neatly with the goal that I'm aiming for. Now I need to show that B1 is sigma of V1. Are you ready? I need B1 to be sigma of V1. Why don't I figure out what sigma of V1 is? Sigma of V1 is therefore going to be this of V1. So it's going to be B1 phi 1 of V1 plus Bn phi n of V1. And phi 1 of V1 is the coefficient of V1, which is 1. And phi 2 of V1 is the coefficient of V1. So phi 2 of V1 is the coefficient of V2, and V1 doesn't have a V2, so that coefficient is 0. And so I get B1, and therefore B1 is sigma of V1. And similarly for all the other ones.
We know how a function works on its basis. That means we know how it works in general. While
so yeah, you're saying that the whole point of linear functions is that you can apply them to things that you get by adding stuff and combinations, and so you only need to know what it does to a basis. Just repeating what you said, just to make sure it's on the recording. And so it's not unexpected to try and figure out what it does to the basis. But on the other hand, from a proving point of view where you're not thinking clearly enough to be able to think, I should probably figure out what it does to the basis, though that's a useful thing to add to our list of tools for linear algebra, I can at least go, I need to get a sigma of V1 in my final answer, so let's figure out what it is. At least you know where you're headed. But if you didn't know what you were trying to prove while trying to prove it, which is how mathematicians really work, like you don't always know what the theorem is that you're trying to prove, you're just trying to figure stuff out. So if you didn't know what we're aiming for, figuring out what sigma of V1 wouldn't have been a bad idea. And then you would have gone, oh, cool, it's the coefficients. And then that would have made your theorem, and you would have said, right, cool, theorem, this is what works out. Yeah. Yeah. Right, so in the previous theorem, well, okay.
the previous theorem, we applied it to the fixed. That's why, yeah, that's how we.
So you, oh yeah, okay, so you did sigma of V1. Okay, so this proof is actually contained in the other proof. So in the other proof, you just picked a vector, a function in V star, and you did sigma of V1, and it turned out that it was also, you could construct sigma as that number times phi of 1.
We wanted to sort that.
Okay, cool. Yep. So if you wanted to show that it really was a spanning set, you would have to show that no matter what you pick could be written as a linear combination of the other things. And just a second. And so you'd let sigma be in V star. And then you'd say, all right, well, I know that sigma of any vector, which is a linear combination of v1 up to v, is guaranteed to be a1 sigma of v1 like that. And so if I knew what sigma of v1 was, I'd be good. Yep. So that's just the reasoning. Because I need to know what it does to everything in order to know what it does, but I only really need to know what it does to the basis. Yep. And so, and A1 is phi 1 of this thing. All right, just a second. Let V be in V, then V is equal to A1 V1 plus AN VN for some ANs. And so sigma of V is equal to this, which is phi 1 of V Yep. Cool. Ah, not there yet. Now what? Is that enough? Oh, and that's it. Oh, wow. That's so cool. Sorry. It's already done. So sigma of V is sigma of this, because linear transformation this. And A1 is phi 1 of V, because that's how phi 1 works. Nothing up my sleeves. This is sigma of V1 phi 1 of V plus sigma of Vn phi n of V. So sigma of V is this linear combination of the phi i's of V. And so therefore sigma must be sigma V1 phi 1 up to sigma Vn phi n, because I can remove all the V's because it does that to every V. Because this V ends up in all of these positions and they are functions of V, and these are just numbers. Yay. That was a sweet ass magic trick. And so this simultaneously proves, so the other one was, assume it is a basis, proves that that's the right number. But this is simultaneously showing it's a basis and showing it's the right number, all in one go. Ah. Which is a linear combination of phi 1 up to phi n. And actually, it's the only linear combination it could be, and therefore they must be a basis because everything has a unique representation. Ah. Yes, you have to start with that. So you have to start, assuming. But you needed V1 up to Vn to be a basis in order to define phi 1 up to phi n in the first place. Yeah. Oh, that's so cool. That is so cool because you almost did nothing. It's like, oh, look, it's the thing I wanted. And so technically there's a few extra words to make it a proper basis. At the moment, we've just shown that technically, so sigma is a linear combination of phi 1 up to phi n. So it certainly spans V star, and you'd have to show that they were independent, or instead of showing they're independent, you would just have to show that there was a unique way of doing it, because that would make it a basis as well. What's that? Oh, the dimension's the right dimension. Oh, okay, cool. Yeah. Because the three things, right? There's the definition of basis, which is they're independent. they're span and they're independent. And then there's the definition of dimension, which is it has the right number of vectors for the dimension. And if any two of those are true, it's a basis. Yeah, cool. Oh, that's just gorgeous. Yeah. But, I mean, your comment about liking we spend an hour trying to make sense of all the little bits, that's what pure maths is about. Like really trying to make sense of all those bits, which means it's a big ask to design a pure maths course. It's actually really hard to teach because you actually need to spend this sort of time that we've been spending today really working through what the hell every symbol means and how it does it. And you sometimes have to do it the long way for the short way to make sense. And actually it was, I really like that it was really good for us to try and do the proof of the second one without having seen the proof of the first one, to see where that really came from. And plus this is how the orthonormal basis proof works in Maths 1B. Yeah, so what this is actually telling us is that you can use as a basis for the linear functionals orthogonal projection onto each of the axes as your basis. Because that's what orthogonal projection onto the x-axis is. It tells you the x coordinate. So that's just, but yeah, this is the move that you do when you prove that when you do orthogonal projection, the coefficients are the dot products of the orthogonal basis vectors with the stuff. It's the same move that you do. You do the dot product with all the things and all the bits cancel out and you get the bit you want. Yeah, so it's cool. It's cool. Yeah, I can stay for a bit. Oh, try proof live. Yes, let's do proof live. Sorry? All right, I'll take a photo and then you can have your computer back. This question 2 here. This let H be a normal subgroup.
Yeah.
Let H be a normal subgroup of G with index M. Prove that G to the power of M is in H for every G in G. So I'm presuming these groups are written multiplicatively as opposed to additively. That's the tradition. Yes. Yeah, that's the tradition, right? Okay. Correct. Excellent. First move, what does it mean? Okay. So we don't have to say suppose. It's not an if-then statement. I mean, it technically is if, all of this is the if, but it's not written as an if-then, it's just a thing. So so H is normal in G. And is this how you write it? Might as well write it in the proper symbols. And so you're saying, what does this mean? This means that the number of cosets of H in G is M. Yep, okay. I guess it also means that the size of the group G factor H is M. because that's how many elements it has. But I don't know if that's helpful. Okay. So our goal is to show that for every G in G, G to the power of M is in H. So that means we start with something that's in G, do some working, and conclude that G to the power of M is in H. So we're going to say let G be an element of G. Working, working, working. Somewhere at the bottom, somewhere, possibly on a whole extra page, there will be, therefore, G to the power of M is in H. That's the thing we've been asked to prove. Our proof will look like that. If we're going to do proof by direct proof, it seems reasonable to me to do it that way. Okay. Well, I have to talk. I mean, there's cosets everywhere. I need to talk about cosets, right? That seems reasonable. So G to the power of M being in H would be that G to the power of M H is H in a coset sense. That would be the line before. That's if I could make this conclusion, and the only reason I'm thinking of that is that I've got cosets, and so I'm thinking of a coset way of making this decision. Okay, and a coset way of doing this would be GH to the power of M. So, that's what this is. So I'm thinking that I need to make statements about GH to the power of M and show that it's the same as H. Am I allowed to use the theorems about the orders of elements dividing the orders of groups?
Yes. And
No, I don't need that. That's not what I mean. I don't know what that means. No. I want what are you saying? Hmm? Just a second. This thing? Yep, that wasn't my plan. My plan was to ask a question about groups at all. G factored out H is a group. And GH is an element of that group. And H is the identity of that group. I'm trying to show that GH to the power of M is H, showing that a power of an element of a group is the identity. That means I'm trying to show the order of that element is M. That's okay. The order of that element divides M. And the order of an element has to divide the order of your group. It's one of the theorems. I don't know, it's got a person's name to go with it. Oh, maybe it comes after this though. Yeah, Lagrange's theorem. The order of H divides the order of G. Oh, it's not there. I'm annoyed. Okay, we're gonna have to do it ourselves. Yep, that's what I was looking at. So when you do the powers of an element, you make a subgroup. Right, you've got G and G squared and G cubed and the identity and all of the powers of G. That's a cyclic subgroup generated by G. And that subgroup also has to divide the order of its group. So GH's powers have to divide the order of H. That's my guess at what's going on in this proof. Could be wrong, but I'm squarely putting myself in Coset land. I'm going to consider GH and not worry about the group itself at the moment, because everything has to come from the cosets. Well, I don't know if it has to, but I'm going to assume it has to. Let's consider the subgroup generated by GH. This subgroup is a subgroup of G factoring out H. Not all the other cosets. I'm just, whatever cosets this produces when I do its powers, together they are a subgroup of G factoring out H. So in my head, here's G, and here's H here, and these are the cosets, and here's GH, and GH squared might be this, and maybe GH to the, so here's GH squared, here's GH cubed, and so on. Might not be all of them, just a second. Here's GH squared, here's GH cubed, and then GH to the power 4 is H again, for example. And so these four things are a subgroup of the factor group. Yeah. You multiply everything in H by everything else in H. Yeah. Correct. But GH is an element of the factor group, and the definition of what GH times becomes GH. Yeah. So it is a subgroup of G factor H, which means its order divides the order of G factor H. Which is M. I'm just guessing here, so I'm just making it up, but okay. Is this how you did it? Okay. So GH, the cyclic group generated by GH divides capital G factored with little h. The size of it anyway is M. And the size of this is the order of GH. It's the biggest power that produces the identity. The smallest. It's the smallest positive number n such that gh to the n is the identity and that number divides m. So m is n times something, right? Some k. So g to the gh to the n to the k is h to the k. So gh to the nk is h to the k. And so therefore gh to the m is h. And therefore gmh is h, because that's what gh to the m is, it's gmh. There's probably another way. So I'm switching my perspective from g to g factor h. And the elements of g factor h are cosets. I would like to show that the coset gh to the power of m is the same as h. Which means I need to show a power of this element is the identity. Because this is an element of g factor h. H is the identity of g factor h. And to show a power of an element is the identity, I need to show that the order of that identity divides m. So that's what I was thinking. So I'm going back to here. Consider the I need to show that g h to the m is h. Pardon me. Anyway, so the cyclic group generated by GH is a subgroup of G factor H. Therefore, by, is it Lagrange, was it? Therefore, by Lagrange's theorem, the cyclic group generated by GH divides the size of this group divides the size of this group, because that's Lagrange's theorem. Subgroup sizes divide the group sizes. Official word's order, isn't it? Order of a subgroup divides the order of a group. Now, the size of the cyclic group is the smallest positive number n such that g to the power of n, such that element to the power of n is the identity. And our element is gh and our identity is h. And we just proved that this number divides m. And so it must be a multiple of m, it must be a multiple of n. And so I'm going to do this to the power of the correct number that will produce m. And so I'll do it to the power of k. And so I've got gh to the power of nk, which is gh to the power of m. It's h to the power of k, but h is the identity, so that's just h again. And gh to the power of m is g to the m times h, because that's how cosets work. So gmh is h, and therefore gm is in h, because that's how elements pass from cosets. This may not have been the original plan. Ah. So I switched my perspective from the original group to the group that is the cosets. And I'm allowed to say things about the cosets that I'm allowed to say about individual groups. And so elements become cosets, the identity becomes the subgroup H. Yeah. I'm pretty sure there's a corollary to Lagrange's theorem that says the order of an element divides the order of a group. Yeah, okay. But I'm just proving that that this is more or less this bit here is the proof that the order of an element divides the order of a group. But I just couldn't find the theorem. Did you find it? No, that was something else. Yeah. Correct. But I meant the order of an element, as in the smallest power you need to make it the identity, divides the order of the group.
Or you can just say they're all.
Yeah, that's right. So, but when I did Algebra 2, it was a corollary. It was a theorem of its own. Yep.
Definition 5.5 says that statement become a subgroup determines the number of like complex. The second includes the subgroup itself.
Yes. Yep. H is a coset of H.
So when that says that there are in process involved, including so that in a sense means that H is power of everything H or
Yeah.
any power of everything H to the power of everything.
Yeah. So any element to the power of the size of the group that it's in is the identity. Definitely.
If you were writing this properly, you probably would have write H to K, you would write E to the K.
No, H to the K. Yep.
I thought you can't apply to
No, I'm doing powers of the element of the factor group G factor H. So I can say EH to the K if I want, but like H is a subgroup, but it's also an element of another group. And this is one of the big switches in group theory that we make, where we go, oh, a subgroup is a subgroup, sure, but it's also an element of another group, which is the factor group. Yeah. Which is just a real big switch that we make. We go, oh, hi, okay. So technically, what I've drawn here is I could actually make a factor group of this group inside this group as well. And make cosets of the cyclic group generated by the coset GH in the factor group G factor H. And so I can make a new factor group, G factor H, factoring the cyclic group generated by GH if I wanted. Turtles all the way down, people. So, yeah. I'm sure there's another way that it's less coset-y, but you have to use the coset somewhere. Because I could imagine doing all the powers of G in one direction. No, I can't. No, I'm not going to. Okay. Yeah. But whoever marks this needs to be flexible enough to deal with this, because your lecturers have been flexible enough to deal with this when they do the content. This is one of the big things. If I'm allowed to write this, then I'm allowed to write this. If it made me feel better, I could do this. It feels ever so slightly circular reasoning, because I know that Lagrange's theorem requires you to know that the coset partition the original, and so I feel like there's, I don't know, it's right on the edge of me being comfortable. Like I just, oh no, this it's like using It's like using L'Hopital's rule to show the fundamental trig identity, but you need the fundamental trig identity to show L'Hopital's rule works. Sorry. That is because so we're okay here to jump from here to here?
Yeah.
Okay. So this is coset multiplication. Yep. And when you multiply two cosets, you multiply them the representatives of the coset. And so this is going to be like that. That is how coset multiplication is defined, yes. And it is well defined, because even if I had chosen different representatives, I would still have worked. Yeah. But it's not just how it's defined. It's defined that way because it works. Like it can't not work, so we're allowed to use it. But this is a perfectly reasonable reasoning as well that makes it really much clearer what's going on. All right. And this all works because it is a normal subgroup to begin with. And so GH is the same as HG. So any one of these I can switch. And then the H's are together. And so the H times H is H. Yeah, that's another way of thinking about it. Yeah. All right. Rightio. I didn't get to talk about bilinear forms, I'm sorry. But I choose to stop.
Yeah.